I want to welcome you to my lecture today. Of course, today I'm actually going to be walking you through another exciting statistical topic. Of course, I told you the other time, statistics is like a story, okay? A story that goes on and on and on. Okay, give me 1 second. I'm actually going to share my lecture slide. Okay, so this is my lecture slide. Today, the focus is going to be on multivariate normal distributions. And of course, in the outline, I'm actually going to walk you through the derivation of the joint conditional and the marginal distribution of, we're not going to go into multivariate, but we're going to look at the special form of the multivariate that we'll call the bivariate, okay, normal distribution. I'm going to walk you through how we derive the expectation, here, how we derive the conditional expectation of a particular variable given the other variable. Also going to walk you through with the variance, the conditional and the unconditional variance as well. And of course, application. But before I actually go into this topic, of course, before now, you've been introduced to different types of probability distribution. We actually classify them as, discrete type and continuous type. Of course, under the discrete type, of course, I've walked you through the Bernoulli binomial, hypergeometric, the negative binomial, and the like. And of course, under the continuous type distribution, I walk you through continuous uniform. We did a normal distribution. We did exponential, gamma, and so on like that. But you know what? Every other stuff that we've been doing before, we've actually been focusing on variable of one measurement. But right now, okay, what we started on Tuesday, we'll be focusing on situation where we have two observable measurement. We have like two events occurring simultaneously. And of course, before now, I've introduced you to jointly distributed random variables. Okay. And I remember yesterday I walked you through the expectation, okay, of, the jointly distributed function. Okay. Of course, the jointly distributed function could be a PMF or a joint or PDF. Of course, I walk you through all of that. Now also remember that I also walk you through the expectation, the conditional and the unconditional expectation. But you know what? I've already given you an idea of what we're trying to do. What we're basically trying to do is we have two variables, and these two variables, that are occurring, they are being observed simultaneously. Okay. And what I want to walk you through today is a situation where a particular variable follow normal distribution. Okay. So, and the other one follow normal distribution. Of course, what I want to walk you through now, the two variables are jointly normally distributed. Okay, that is what I basically want to walk you through. Now take a look at this. But before we go into that bivariate, normality, let's first look at the idea of a normal, distribution. Of course, I told you the other time, in statistical analysis, of course, the effects of, or let me just say, uh, the uh, the significance of normal distribution cannot be overemphasized. When we talk about as well as statistics, is concerned. Okay, so this is the idea. This particular distribution that we call normal distribution was actually developed by the movers. Okay, I told you the movers actually use a normal distribution as approximation to binomial. Okay, and in 1783, okay, we realized that Laplace now applied the normal distribution to measurement error. Okay, in 1809, okay, somebody called Gauss applied normal distribution, okay, to the study of astronomical data. Okay, and let me just say, from them, a lot of researchers have started, applying normal distribution to depict real life practical situation. We got a lot of biological phenomena that can actually be captured by normal distribution. Okay, so if I'm focusing on a variable x, like now I'm focusing on variable x. If variable x is blood pressure, okay? Now, the reason why a normal distribution can actually be used, okay, to model that is because when you take a look at a large population, okay, few, we basically have low blood pressure. Few, we have, large blood pressure, okay, why the majority, they basically going to have, their blood pressure is basically going to be very close to the average. And if you take a look at what I showed you the other time about, the architecture, okay, about the shape of a normal distribution, okay, the shape of it, what make it to be more applicable, in real life, what make it to depict some real life phenomena is because of the double barrel shape. Okay, I told you the other time, if this is the center, this is the average, right? The few, we have a low blood pressure, right? Few, we have a large blood pressure, right? And majority, we have blood pressure very close to the center, to the average. And that is the reason, because of that, because of the double bear shape and the symmetric nature of the normal distribution can actually depict that. Okay, so I think I've walked you through that before. So if you take a look at when S follow normal distribution now, okay, when S follow normal distribution, okay, with two parameters, mean and sigma squared, which is the mean and the variance, okay, then this is the statistical architecture that is going to be called the probability density function of a normal distribution. So what you are saying that right now is a univariate normal. Univariate, univariate normal, because we're only focusing on one variable. Okay, I wanted to take a look at that. I've walked you through all this, okay, the kind of statistical inference you can draw, okay, from this. Okay, now what of in a situation where we're no longer talking about one variable that is distributed normally? What if we're talking about two variables now? Okay, we got two variables now distributed normally. Okay, that is the statistical architecture. Okay, so this is what we call a joint normal distribution. Okay, I wanted to take a look at that. This is the joint. There's something that I need you to pay attention to what you are seeing now. I got a variable x1. It has a mean of mu1, and the variance is sigma 1 squared. I got a variable x2 with a mean of mu2, and the variance is sigma 2 squared. Okay. Now, when you take a look at this guy now, that's what we call correlation, rho. Okay. When rho equal to 0, it's basically going to say x1 and x2 are independent. Because if I plug in rho, if I plug in 0 for rho, okay, here, wherever you see rho, all what you're just going to see is just going to be the products of two univariate normal distribution. where the first univariate normal distribution is going to be for x1, the second one is going to be for x2. Now, some of you may want to ask, what is the significance of a joint normal distribution? So why not just using univariate? Why do I actually need to represent, x1 and x2 in probability distribution in terms of this? I'm going to tell you now. We got a lot of benefits, using the joint. Number one benefit, okay. For instance, let's say x1 is height and x2 is weight. The doctor may want to believe maybe there's a connection, there's a relationship between height and weight. Okay. In a situation where there's a connection between height and weight, the correlation value is not going to be equal to 0. And that will enable us to see how closely, okay, they actually change over time. If I want to look at how closely the x and y, the height and weight, okay, actually changes together over time, I'm basically going to be talking about the covariance. I know you've heard about covariance before. The idea of the covariance will tell us direction of the relationship. It's going to tell us how closely they actually changes together. But it's not going to tell us the magnitude of the relationship, so that from the covariance, we can go into the correlation, because the covariance is a standardized, when you standardize covariance, okay, you're actually going to get correlation. If you take a look at this guy here, okay, let me use my pen now. If you take a look at this, the numerator here is a covariance that I talk about. Okay, now if I want to get a correlation rho, okay, I'm actually going to divide the covariance by the product of the standard deviation of x1 and x2. So which means I'm standardizing covariance. When I standardize covariance, I got correlation. And of course, you know what correlation measures, right? Correlation measures, the direction and the strength of the relationship between two variables. Take a look at all of that. So the idea of the joint distribution now will enable us to investigate whether the two variables are connected. And I say connected like height and weight, okay? So that will give us that opportunity. And not only that, we're also going to have an opportunity, let's say I'm just assuming now, okay? I'm assuming now, if x1 represent, like for instance, we got two group of patients, okay? A group, one group A, group B. They're actually suffering from the same terminal disease, maybe cancer. And what we basically subject, maybe group A, we give them combination of physiotherapy and chemotherapy, but group B, we only give them chemotherapy, okay? Now, and I want to compare the survivor times. Let me now assume now that the mathematicians or the statistician, okay, actually, trying to model, he discovered that the survivor times for patients who undergo the combination of physiotherapy and chemotherapy, okay, let's say we actually refer to that like the survivor time as x1, okay. The survivor time for the x1 represents the survivor time for the group that receive chemotherapy and physiotherapy, and x2, okay, and x2 is the survivor time okay, of those that actually receive only chemotherapy, okay, I want you to take note of that. Okay, now we got X1 and X2. Okay, now you may want to find what is the probability of X1 greater than X2. Okay, give me 1 second. I'm gonna, okay, I'm gonna rewrite that. Why is it? I'm gonna see why that is. Let me put it here. Okay, the probability of X1, the probability of X1 greater than, give me 1 second, I'm gonna use a different one. I don't know why that is, oh, I think I'm the one crossing that. I'm gonna take a different pen now. Before first cancel all of that. And take a different pen. Is this gonna work? Okay, this is working now. Why is it giving me all of that? So the probability of X1 greater than X2. Okay, so I want to find the probability of X1, greater than X2. Okay, if I really want to get that, just like what I said, okay, the probability of X1 greater than X2. Okay, what is the probability that a particular group will have more survival time than the other one? If I want to answer this question, of course, I need a joint. Okay, I just want to take note of all of that. Now, what I'm trying to show you now is to tell you that if you make a plot of this particular distribution, okay, where mu1 equal to mu2, okay, equal to, mu equal to 0 and sigma 1 equal to sigma 2 equal to 1 and rho equal to that is what you're going to get. You can try that. Okay, and don't also forget the mu1 is expected value of x1, mu2 is expected value of x2, and sigma 1 square is the variance of x1 and sigma 2 square is that. And I just walk you through the correlation right now. Okay, you know what we want to do now? Do you know if you want to follow by the idea, what we actually do the other time? Okay, if you want to follow the idea, if you take a look at this guy, right? I have a joint and I basically interested in X1. Okay, then all what I'm going to do is to integrate that with respect to the variable X2 that I'm not interested in. You remember I said something like that the other time. That is exactly what I'm doing here. That's what I'm doing here. Do you see that? That's what I'm doing here. I put a joint normal distribution now, and I want to integrate with respect to X2. Okay. Now, after that, the next thing that I actually want to do is to simplify. So if I want to simplify, you can see here we got, let me use my, what is it called? I'm going to use my pointer now. Now, when you take a look at here, got a sigma 1 squared, sigma 2 squared, sigma 1, sigma 2. Okay, the SCM is basically going to be sigma 1 squared, sigma 2 squared if I factorize that. Initially, this is what we have. I bring this guy and this guy out. This is what I'm going to be left with algebraically. Okay, now, the moment you get here, the next thing you're going to do is we're going to add and subtract this guy. We add and subtract this guy. If you take a look at this guy, it's what you have here now. It's what you have here. You are adding and subtracting, okay? Because we basically want to complete the square in the exponents, okay? Now, when you do that, this is what you have. Now, if you have this guy now, okay, the next thing that you actually gonna do, okay, if you take a look at this, the two of the, or let me just say, let me go back. If you take a look at this, right? And let me see other things that resemble that and this guy. You see the two? I basically want to combine them. Okay, I want to combine the two. Like I said, I'm combining this and I'm also combining this. So when you're combining that, you're going to be factorizing, right? You're going to be factorizing. Okay. So when you factorize now, you're going to see that what is common, right? What is common is x1 minus mu1 or squared and sigma 2 squared. Okay. When you factorize that out, this is what you're going to have. Give me 1 second. This is what you're going to have. Give me 1 second. I think that is, okay. You're basically going to have this guy. Okay. When you do the factorization, that's exactly what you're going to have. You're going to have this guy, right? Okay. Which means you've already, what you've done, you've combined, you factorize, you combine this guy and this guy. And that actually give you this. Every other thing is still intact. Okay. This is what you have now. Okay. Now, the next thing now is to now simplify further. Okay. If you want to simplify further, if you take a look at this, right? Okay. You take a look at this guy now, right? It's what we still have, right? Okay. Now, because I'm integrating with respect to x2, is there a way I can figure out a constant term that doesn't depend on x2? If you take a look at this guy, you see this guy, is there any x2? There's no x2, right? Okay. And don't forget, it's on exponent. You know that everything here is on this exponent. So when I bring that guy out, that's what I have here now. You see it there now? I'm actually going to be left with, I'm going to be left with this one. Okay. When I bring this guy out, I'm only going to be left with this. And you know what? When I'm left with that, okay, you're basically going to see that this guy, okay, we can actually write it in form of a minus b all squared. A minus b all squared. Okay, a minus b all squared. Okay, you can write it that way. Okay, a minus b all squared. Okay, now if you do that, this is it. This is the all squared that we talk about. This minus that all squared. So we are here now, right? Okay, so when you continue to go from here to, if you take a look at this, let me use my pointer. If you take a look at this guy, is this guy, right? This guy now is still this guy, right? This guy now, you simplify sigma squared, 2 square cancel sigma, 2 square, 1 minus rho square cancel that. You are left with this. Now, this is what we have now. Okay. Now, you may be wondering, how do we get this guy? Don't forget. Okay. If we have this guy here, okay, and if I want to factorize out, okay, I can do like sigma 2 square over sigma 1 square. Take a look at this. So here, this is C here. You can see it here. So if I want to write that, I can just take the sigma 1 square up, because of the square here. This is sigma 2 squared. And I can borrow from the sigma 1 square to go up, so that we're going to have sigma 2 squared divided by sigma 1 square, which is this one. Because sigma 2 over sigma 1 all square, you can see that. Then we left with this. Look at that now. It's taking shape, right? Now, the f of x1, you continue to go all the way. in such a way that in the end, when you make an attempt to make rho to be equal to 0, when rho equal to 0, maybe you believe that x and one, s1 and x2 are independent. Of course, you're going to end up here. You're going to end up here, which is a univariate now. But you know what? That's not where I'm going. Where I'm actually going is what of in a situation where I'm looking for a conditional function, f of x2 given x1. Why am I interested in that? Maybe I want to find the probability of the survival time, based on the example that I used the other time, the survival time of the group of patients that receive, a certain medication. We want to figure out the probability of the survival time, maybe greater than 5 years, given that I already know the survival time for the other group. That's a conditional function that I need here. So, but before you do the conditional function, this is the formula that we're going to use in deriving that. F of x2 given x1 is going to be the ratio of the joint to the marginal. This is the joint normal density for x1, x2. And this guy now is the marginal, which is the univariate. Okay? Now, all what I'm just going to do now is to simplify this, If I basically want to simplify this now, okay, combining this with this, that will give you this, if you do your algebra very well. And exponential raised to power negative this is going to go up and match with this exponential, and it's going to be becoming a plus. This is the plus. Can you see now? You see the entity? Moving this guy up. I told you you're going to combine this guy with this guy, and that's going to lead to this guy, right? And the exponents, okay, you're going to combine the exponent here with the exponent here. This is a negative, right? There's going to be a positive. Take a look at that. Now, this is where we are now. We are actually here. Excuse me. Now we're actually here now. Oh, give me 1 second. Okay, so we're actually here now. So what we're going to do now, we basically, putting time involving x1 minus mu1 all squared together by multiplying and dividing last time by this. Okay, if you do what I actually said here, you're going to find yourself here. Okay, and when you simplify, because take a look at this, 1 minus into that, when you expand that, this is only going to give you rho squared, because the 1 and 1 is going to cancel out. So this guy now, the resulting expression for this is here. This guy is here, and the one in the middle is the intact, is right here. Now, this is where we are now. Don't forget, what are we doing? We're trying to, figure out the f of x2 given x1 using the bivariate normal density. Now, this is where we are now. Now, the next thing that we basically are going to do is, when I find myself here right now, okay, now, by the time pulling out the sigma 2 square in the denominator, initially, there was a sigma 2 square here, right? Okay, if I bring it out, if I bring this guy out, automatically, I'm going to do some math here. I'm also going to do some math here. Let's make an attempt. Bring a sigma 2 square out. Breaking it out, okay, it's no longer here, right? I got to do some math here. Of course, we don't expect this guy to be the same, bringing this guy out. It's more or less like, if I bring this guy out now, I'm also bringing it out from here. I'm also bringing it out from here. That's what it implies. And don't forget the fact that rho here is a covariance divided by sigma 1, sigma 2. So I'm going to have this expression now. Okay. I'm going to have this expression now. When I have this expression now, oh my God, this is a squared. The whole of this guy is a squared. If you take a look at this guy is squared, this guy is squared, this guy is squared, this guy is squared. It means I can rewrite this guy like x1 minus mu1 parenthesis rho is sigma 2 divided by sigma 1 and put all squared. And this guy is already squared. Do you know the whole of this can actually be written as this guy here? Where we got a square here, just more or less like you have a minus b all squared in math, where you're going to be a squared minus 2ab plus b squared. That's exactly what you have now. Take a look at that. Okay, now we are getting to the finishing line. Okay, now I can rewrite this guy as this guy. You know, when I have s2 minus mu2, I can just, okay, let's mu2 also go with the whole of with this one mathematically. I can put a negative out. Negative times mu2 is negative mu2. Negative times plus is this. No, I see, no, this is still this. Now, right now, this is my final expression. Okay. Now, what I'm trying to tell you now, give me 1 second. So what I'm trying to what I'm trying to say now, this guy that I have now is actually the conditional probability function of x2 given x1. Okay, I derive that all the way from using the fact that the conditional function is basically equal to the ratio of the joint to the marginal, as you can see. Okay, now what I want to do, what I have now, okay, this is actually, okay, what I have now. Okay, now if I have this guy now, I want you to pay attention to something. Okay, I want you to pay attention now. If I have a distribution like this, how will I figure out what is going to be the mean? When I say mean, I make conditional mean. What is going to be the expected value of x2 given x1, because this guy now is a function of x2 given x1. So how am I going to get the expectation of x2 given x1? Not only that, how am I going to get the variance of x2 given x1 as well? But you know what? There's a way we're going to write it out from here. But I first want you to see univariate. Now take a look at this guy. Okay. If you take a look at this guy, this is a univariate, right? Okay, I need you to pay attention to this. Okay, in a normal structure, okay, mu, anytime you see something x minus mu, it means whatever that is here is the mean of x. Now, when you go into the square roots, anything other than 2 pi is the variance. What is anything other than 2 pi inside the square root? That's sigma square, right? That will be the variance. And that is the reason why when x follow normal distribution, we know the mean is mu, the variance is sigma square. I needed to pay attention to this because we're also going to use by way of induction to be able to figure out what the conditional mean and the conditional variance is going to be. So take a look at that. Now, I said mean is going to be whatever you are subtracting from the random variable x, and the variance sigma squared is anything other than square root of 2 pi, like anything other than, inside the square root 2 pi, anything other than 2 pi, that's actually sigma square, right? Now you're going to see now the one we derive, okay, we don't forget this is f, give me 1 second. This is f of x2, okay, given x1, okay, f of x2 given x1. Okay. Now, give me 1 second. I'm going to stop my share. I'm basically going to reshare that. I want to correct something here, give me 1 second. I don't like the idea that marker is kind of misbehaving. Okay, so let me force erase all of that. Okay, now when you give me 1 second. Let me cancel this guy first so that I can actually project a different one. That's okay. I think I'm gonna share my screen now. Okay, that's okay. Now what I'm trying to say, in essence, is okay when you pay attention here. Now, if you want to do the same, here, okay, if we basically want to do the same, the mean of x2, whatever that appears after subtraction, the whole of that is going to be the mean. Okay, I want you to take note now. What I'm trying to say now is that was why this is the mean. Okay, so this guy is the mean of x2 given x1. That is what you are seeing here. Now, the other time I said go back to the square root. Anything other than 2 pi. What is anything other than 2 pi is sigma 2 squared 1 minus rho squared, which is why the conditional variance is this guy. Okay, so I need you to pay attention to that. So what am I telling the world? What I'm telling the world now, okay, what I'm telling the world is that, the distribution now is going to be the x2 given x1 is going to follow normal distribution with the mean of this and the variance of that. And do you know, for those of you who are familiar with regression analysis, this is the regression of x2 on x1, where you are actually want to figure out what is basically going to be a predicted value for x2, given that you know something about x1. In that case, x2 is going to be dependent and x1 is going to be independent. So as you can see, this is a distribution, okay? And do you know, in a situation where x2 and x1 are independent, you expect the f of x2 giving x1 to be f of x2, right? And in that situation, the conditional mean will become unconditional mean. How? If you plug in rho to be equal to 0 here, what are you going to have? It's just going to be mu2, which is going to be the mean of x2. What if the rho equal to 0 here? What you have, sigma 2 squared, is going to be the mean of x2. I mean, the variance of x2. Take a look at that. I'm going to say that again. When you plug in rho to be 0, that is when correlation equal to 0, which means x1 and x2 are, they don't have relationship. Okay, in that situation, we expect x2 given x1 to be the same as x2, then the mean is just going to be mu2, the variance is just going to be sigma 2 squared. So please take notes. Okay, now what is the summary of the results? Today, I've presented the joint normal distribution where x1 and x2, they follow normal distribution, as you can see. Okay, x1 and x2 follow normal distribution. Okay, they are jointly distributed, and that is the reason why we don't use a separate normal density function. We're using the joint, and there's always benefits using the joint that will enable you to figure out if they are connected in terms of investigating relationship. And not only that, you can actually figure out what is the probability of x1 greater than x2 or x2 greater than x1, stuff like that. that I talk, when I gave an example of survivor analysis the other time, where you want to compare the survivor times of two different group of patients that have terminal disease. Okay, so this is the univariate normal for X1, univariate normal for X2. And if X1 follow normal distribution, of course, you know that they're going to have mu1, the sigma 1 square, when S2 follow normal distribution, it's going to be mu2 sigma 2 squared. And of course, I derive the conditional density. This is a conditional density, f of x2 given x1. This is a conditional density, f of x1 given x2. And, based on this, I can make a conclusion about, what is going to be the mean of x2 given x1 and the variance of x2 given x1. Okay, and of course I told you this guy here. Okay, everything here apart from x2, this guy here is the mean of x2 given x1. And that's what you're saying here. We're talking about x2 given x1. This is the mean. Okay, and this guy is the variance. For x1 given x2, this is the mean. And this guy is the variance. And I told you how you can actually deduce this guy from here and how you can deduce this guy from here. The same way you actually deduce that, okay, from this architecture now, okay, the mean of x1 is mu1. And the variance is sigma 1 square, anything other than 2 pi in the square root. The same thing here. So the same way you're also going to talk about this guy. If I want to figure out the mean now, the mean of this guy is basically the whole of this guy. Anything other than x2 minus that, this guy now. Okay? That's why you're seeing it here. What is the variance? Anything other than 2 pi in the square root, which is sigma 2 squared 1 minus rho squared. And that's why you have that. And you know what? This guy and this guy can be x2 if rho equal to 0. And this guy can be x1 if rho equal to 0, which is a correlation. Okay, I'm going to go into an exercise now. Some of you may be wondering, if I actually want to make use of the normal density. Okay, now, if x1, x2, be jointly normal random variable, with parameters, you have the mean and variance, mu1 given as 1, and sigma 1 square given as 1, the mu2 is 0, the sigma 2 square is 0, and the rho equal to 1 over 2. Now you want to find the probability of 2x1 plus x2 less or equal to 3. And they also will ask you to figure out the covariance of that. And of course, they also ask you to find the probability of x2 greater than 1 given x1 equal to 2. Okay, so how are we going to find this? I'm actually going to show you now. Okay, what I'm going to do, I think I'm actually going to take the picture of that. And when I take the picture of that, then I can share my whiteboard. Okay, so I'm basically going to share my whiteboard now. Okay, if I really want to solve that problem. Okay, now you've already been given mu1 to be equal to 1. Okay, and they gave you sigma 1 squared, okay, to be equal to 1 as well. And of course, they gave you mu2, okay, to be equal to 0. And you are also given the variance for the variable, for the second variable, okay, to be equal to 4. And not only that, they gave you rho, which is the correlation, right, to be 1 over 2. The fact that the correlation is 1 over 2, you know what that implies? X1 and X2 are not independent. Okay? So if they are independent, we expect rho to be equal to 0. Now, if you take a look at the first question, they wanted to find the probability of 2x1, okay, plus x2 okay, less or equal to 3. If I want to find this, okay, because I'm focusing on x1 and x2 and they are jointly distributed, do you know I can actually let W to be 2x1, okay, plus x2. And if I want to rewrite that, I can actually say, okay, what I want to do now is I want to find the probability of W less or equal to 3 because I've actually used W to denote that linear combination. Now, of course, you know, if I want to answer this question where W is a random variable, and I've been told that they you know, x1 and x2 that actually make up the architecture of W is normally distributed, then it means I'm actually going to be using the idea of a standard normal distribution that we did the other time. So if I want to find this guy, right, I'm actually going to say the probability of Z. Okay, okay, the probability of Z less or equal to W, okay, minus the expected value of W, okay, divided by the square root of the variance of W, okay? And when I do that, you know, whatever that I have here, I'm actually going to go into standard normal table to check that, okay, because the probability of W less or equal to 3 is going to be the same thing as the probability of a Z. This time around, talking about Z score, standard normal random variable, which is going to be less or equal to this. So now I know what my W is. My W is 3, but I don't know what the mean of W and what the variance of W is. So if I want to figure out the mean and the variance of that, what am I going to do? Okay, so what I'm going to do now, let me erase, okay, I'm going to erase this guy now. Okay, now, and I'm going to, okay, now I want to find the expected value of W, right? So which is going to be the expected value of 2x1 plus x2, okay? You remember what we did the other time, okay? Expectation of a linear combination. So this is going to be 2 expected value of x1, okay, plus expected value of x2, okay? You know, the expected value of x1 is actually mu1. Expected value of x2 is actually mu2. Don't forget that, okay? So when I plug in 1 here now, and I plug in 0, okay, 2 times 1, 2 plus 0, so I'm actually going to have 2. So my expected value of W is actually equal to 2. Okay, now that I got the expected value of W to be equal to 2, now I want to find the variance of W. Okay, so I'm going to clean this guy up now. You know, I basically want to find the variance of W. I already know the expected value of W. Okay, now it is, I basically want to find the variance of W now. Okay, so the variance of W, okay, is going to be the variance of 2x1 plus x2. Don't forget, we actually denoted 2x1 plus x2 as W. So right now, this is going to be the variance of 2x1 plus the variance of x2, right? And don't also forget the two covariants. So with the two covariants, because of the 2 here, 2 times 2, I'm actually going to get 4 covariance, okay, x1, x2. Okay, you may be wondering how I got that. If you can actually recall, okay, if you can recall what you've done before in statistics, the variance of x plus y, okay, is actually the variance of x plus the variance of y, okay, plus 2 covariance xy. That is the reason. And of course, there's a 4 here because of the fact that one of the variable has, a weight of 2. So 2 times that 2. So that was why you got that. Okay, now I need to simplify this guy now. Don't forget, we've already obtained the expected value of W to be equal to 2. I'm going to clean that guy up now. I'm going to clean this guy up now, okay? So that we can actually continue. We've already gotten the expected value of W to be equal to 2. So what we're doing right now is figuring out the variance. So, here, this is the same thing as 2 squared, right? 4 variance of x1, okay, plus variance, okay, of x2, okay, plus 4, okay. But when you take a look at the covariance, okay, there's a relationship between correlation and a covariance, where correlation is covariance. Don't forget the ratio of covariance, okay, to the variance, to the product of the standard deviation. Okay, so if I want to substitute for this guy now, it's going to be this times that, right? So which means I'm just going to have rho, okay? Then I'm going to have sigma 1, sigma 2. Okay, so this guy is the same thing as sigma 1 squared, and this guy is the same thing as sigma 2 squared. All of that have been given here. So I'm going to clean up now. So let me clean up. Okay, so I'm going to clean up. Okay, so when I clean up now, okay, so finally, it's going to be 4 into, what was the sigma 1 square given 1, which is the variance of 1. What was the variance of x2? Okay, 4, right? Plus 4. What is the rho? 1 over 2. What is the sigma 1? Okay, if the variance is 1, the standard deviation is going to be 1. What is the sigma 2? What is the square root of that? 2, right? So 2 cancel 2. I think it's going to be 4 plus 4 plus 4. That's going to be 12. Okay, now the variance of W equal to 12. So what I'm trying to say now is sigma W, or sigma squared W equal to 12. What would be the standard deviation of W is going to be the square root of 12. Okay, now I've gotten what I need, right? Expected value of W is basically 2. The variance is 12, and the standard deviation is square root of 12. So what I'm going to do now, if I now want to find, like I said, the probability of 2x1, what did I, let me just check okay, 2x1 plus x2, okay, less or equal to 3. So don't forget, it's going to be the probability of W less or equal to 3 is basically going to be the probability of a Z, okay, less or equal to 3. What is the expectation of the W? 2, right? Then the standard deviation is the square root of 12. Okay, so right now, I'm basically going to have this less or equal to 1 over square root of 12. By the time you check that off from the normal table, you're actually going to get 0.6136. That is the probability. So you can see what we did now. We've used that very idea of we actually use a joint normal density to be able to figure this out. Okay, because of my time, I'm going to go into another example. B, question B is asking you to figure out the covariance of x1 plus x2, okay, comma, then 2x1 minus x2. Okay, so what you're going to do here, it's more or less like you actually want to multiply this one by this one. Okay, so when you do that, when you do x1 and this is basically going to give you 2 co x1 comma x1. Okay, now the next one is going to be co x1 comma x2. Okay, followed by 2 into co x2 comma x1, okay, minus co x2 comma x2. Now it's like x1 times this, x1 times that, the way you always do that. So this is what you have. But you know what? When you have the covariance of x1, x1, that's a variance. Okay, this is going to be 2 variance, okay, of x1. Okay, that's going to be 2 variance of x1. So minus, of course, this is a covariance. So and this is also like I said here, without writing that, let me say, don't forget, I said this is going to be 2 variance of x1, because the covariance x1 x1 and this guy here too is going to be variance of x2. But let me tell you, the covariance of x1 x2 is the same as the covariance of x2 x1. Okay, so if you want to go by what they've given you, it's just going to be 2 minus 1 plus 2 minus 4, because you've been given the variance of x1 was 1, based on what you were given initially. You multiply by 2. Okay, the covariance of x1 x2, you can find that using the idea that I told you the other time, rho equal covariance, okay, of x1 comma x2, okay, divided by sigma 1 sigma 2. You'll be given this, you'll be given all of that, you can just find that out. So that was what I did. In the end, I got -1. That is how you're going to go about that. Okay, the last question that I'm actually going to walk you through, it said, find the probability of x2, okay, greater than 1, giving x1 equal to 2. Okay, the probability of x2 greater than 1. Don't forget, we're using normal density. We're using the joints, normal density. Okay, now if you want to do this, if you want to figure out the probability, okay, you first need what is the conditional mean, what is the conditional variance, because we actually going to use the idea of a standard normal distribution. Because of that, you need the conditional mean, you need the conditional variance. Okay, so expected, based on what we derived the other time, expected value of x2 given x1, okay, is basically mu2, okay, plus sigma, rho sigma 2 x1 minus mu1 divided by sigma 1. You remember? I'm recalling this from the conditional distribution that I derived the other time. So this is the mean of the conditional mean x2 given x1. Don't forget, why is it that that's what I want to use? Because they asked me to find what is the probability of s2 greater than something given x1, which means I'm basically going to be using the conditional function. So this is the mean in the process. Now, if this is the mean, okay, but you've been told that x1 equal to 2. So what I'm going to do now, I'm just going to clean this guy and put x1 to be equal to 2 and just put 2 here. Okay, now you've been given the value of this, you got the value of this, you got the value of this, you got the value of this, you also get the value of this. They're giving you all of that. Okay, now when you plug in those values, at the end of the day, when we simplify that, I'm actually going to get 1. That is the expectation of the x2 given x1 equal to 2. You just plug in, initially it was x1 here, and they're giving you other parameters in the equation. They just plug them in. Okay, now the next thing now is, what is the variance associated with what I just did right now? But don't forget, here it's now, when x1 equal to 2, that's what I'm doing. When x1 equal to 2, that's what I'm doing. But let me first write the formula for the variance. Of course, you remember the other time, it's just going to be 1 minus rho squared, okay, then sigma 2 squared. Okay, and don't forget, I remember they give you rho to be half, right? 1 minus half squared. And they've given you the sigma 2 squared. I think that was 4. So when you simplify that, you're basically going to have, let me see, what is, that is going to look like 3. Because this is going to give you 3 over 4, right? And 3 over 4 times 4. So the variance is 3, the mean is 1. If the variance is 3, the mean is 1, oh my God. I can find this guy now. It's going to be super easy. You know why? It's going to be super easy finding that, right? So I now want to find the probability of Z now. Okay, don't forget there's a greater than sign here, right? I'm going to put greater than sign. Okay, when I put the greater than sign, don't forget greater than 1. 1 minus, what was the mean? 1 divided, what was the variance? 3. Don't forget, divided by square root of 3. Standard deviation. Do you see that? Okay. Now, if you take a look at this now, there's going to be, it's going to translate into, I want to find the probability of Z greater than 0. Okay. And the probability of Z greater than 0 is the same thing as 1 minus the probability of Z less or equal to 0. Of course, that will automatically give you half if you check the normal table. We're done. That is it. It's super easy. Okay, I'm going to stop my share now, and I'm going to go into the lecture slide. I'm going to return to lecture slide. Okay, so I've done all of that now. Okay, now you can try this out yourself. Suppose that x1 and x2 have a bivariate normal distribution where this, okay, you're given the conditional mean of x1 given x2 to be that, expected value of s2 given s1 to be that. So can you find what is the expected value? What is all this? They can be found. Okay. Okay. So, and I put a solution here. It's super easy. Okay. This is what you have. They gave you this, and they have to find this. But remember from the formula, expected value of x1 given x2 is this guy. You remember? You know, it's more or less like I simplify. You remember that time? If you come back here, okay, x1 divided by sigma 1 times that minus this times that. So it's basically this one. I simplify that. And you've already been given that is equal to this, right? Now you can compare now. If you compare this with this, okay, what is 3.7? The 3.7 is going to be the whole of this, the one without a variable. That was why here, question 1, that equal to 3.7. And if you compare this with this is x2, this is x2, right? The other one is equal to negative 0.15. That's why you have this. Can you see that now? Equation 1 and 2, we know we got that by comparing this with what we are given. Okay. Now the same thing applicable to the second one. In the second one, okay, equation 3 and equation 4. Then when you want to look at, and they also gave you this information, the variance of x2 given x1 equal to 3.64. And you know that from the formula, the variance of x2 given x1 equal to this. So you're going to equate this one to 3.64. Okay. Now that was why we got this. Now, every other thing now is just, to simplify. Now I got this one now. Okay. Now I can go all the way. If I want to use from 2 and 4, okay, from this and this, okay, I can actually, so which is trying to say if I multiply equation 2 by equation 4, then I'm going to multiply this by this. So that's what I'm doing. And that's going to lead to a row square, because why am I multiplying this and this? So that the sigma 1 can cancel sigma 1, sigma 2 can cancel. So that I'm going to be left with a row. That's why you have a row square. So row square equal to that, I got my row to be equal to that. Okay. So if my row equal to that, I can go back to equation 5 to figure out the sigma 2 squared by plugging in whatever I got for the row. Okay, plugging that in now. Okay, and that will lead you to getting the sigma 1 and the sigma 2 squared. Okay, I believe you can actually see that now. Okay, and after you've already obtained that, I can go back to equation 1 and 2. Okay, going back to equation 1 and 2, I'm actually going to, if you take a look at this entity, okay, was negative 0.15. I plug in, I have this, negative is going to be a plus. The same thing here. I can solve these two equations simultaneously. And I'm basically going to obtain my mu1 and mu2. That is the end of that. That's super easy. Okay. Now I'm going to give you this as an exercise where you're going to use the idea of a joint normal density. Suppose that the height of married couples can be explained by bivariate normal distribution if the wives have a mean height of 66.8 inches and a standard deviation of 2 inches, while the height of the husband have a mean of 70 inches and a standard deviation of 2 inches. The correlation between the height is 0.68. What is the probability that for a randomly selected couple, the wife is taller than the husband? Wife taller than the husband. You want to find the probability of X greater than Y. The probability of X greater than Y will be the same. It will be translated to, to the probability of X minus Y greater than 0. Probability of X minus Y greater than 0. You can actually let W to represent X minus Y, which is going to translate to probability of W greater than 0. There, you now need the expected value of W. You need the variance of W. You need the standard deviation of W to be able to standardize that. Use the idea of what I did before. Okay, do this for extra credits. Okay, that is going to be the end of my lecture today. You've been introduced to joint normal density. I've walked you through statistical architecture for that. We've made the derivation. And not only that, I've also walked you through the application. Okay, I've walked you through the application. Okay, in the application was in survivor analysis where I actually let a particular variable represent the survivor time of some patients that were actually giving certain medication, okay, and Y represent the survival time of the other one. You may basically want to find what is the probability that the survival time of S will be greater than Y. What is the probability that, okay, those who receive, certain medication will have an elongated life, more than those who receive the other medication. Not only survival analysis, okay, like for instance, I gave you an example yesterday, where I actually let X to be the driving facility, I mean the proportion of time the driving facility is being used in a bank, and the proportion of time, and Y represent proportion of time the working facility is used in a bank. Of course, if you go to Bank of America, or you go to what is it called, West Fargo and the like, Hutchinson Bank and the like, or you're actually going to see that the two events are taking place simultaneously. Okay, so if I want to figure out what is the probability that the proportion time the working facility is greater than the proportion time the drive-in facility is being used. Not only that, you may want to talk about politics. For instance, if X represent the proportion of, the proportion of votes received by a Republican party, okay, by a Republican candidate for the president in 2016, if you let that be X, and you let the proportion of votes received by, the presidential candidate of Republican Party in 2020, okay, to be Y, and you basically want to find what is the probability of Y greater than X? What is the probability that the proportion of vote received by presidential candidate of the Republican Party in 2020 will be greater than 2016? Of course, in 2020, the candidate was former President Trump, and in 2020, okay, they also presented former President Trump. Okay, we can also use the idea to find, okay, the conditional probability. What is the probability that, okay, if the candidates of the Republican Party in 2016, okay, actually receive this certain number of votes, or proportion of vote, okay, what is the probability that they're basically going to receive a vote greater than maybe 60% in 2020? The idea of the joint can also be used. Okay, there's a lot of wide, application of that. Okay, this is where I'm going to stop. Make sure you stay safe and have a lovely day. Bye for now, everyone.